right, let's dive in. Triangles are literally everywhere, and today we're going to build the ultimate trigonometry toolkit to master them. We're going to break down the most essential rules for right-angle triangles and turn some pretty complex math into simple, powerful tools you can use right away. Let's get to it. So here's the game plan. First, we'll look at the fundamental code of triangles. Then I'll show you an amazing shortcut using what I call triplets. After that, we'll learn to speak the language of angles with ratios. And finally, we'll unlock the master keys of trigonometry with identities. First up, we have to start with the foundation of, well, everything. See, there's this simple, beautiful rule that every single right-angled triangle in the universe has to follow. No exceptions. And this is it, the famous Pythagorean theorem. Now, you've probably heard of it, but what's so important to realize is that this one rule is basically the parent of everything else we're going to talk about today. It's this simple idea that the longest side of a right-angled triangle has a special predictable relationship with the other two. Okay, quick vocabulary check so we're all on the same page. We've got the perpendicular, we've got the base, and then we have the one side that's always opposite the right angle, that's the longest one, and it's called the hypotenuse. Let's just call them P, B, and H. Easy enough, right? And here's that code in its purest, most elegant form. The square of the perpendicular plus the square of the base, it always equals the square of the hypotenuse. This tiny equation right here, it's the key that unlocks our entire toolkit. All right, time for our first pro tip. What if I told you that you could solve for a triangle's sides without even needing that formula? That's exactly where triplets come in. Seriously, this trick lets you solve problems in seconds. So what is a Pythagorean triplet? It's just a set of three nice, clean, whole numbers that fit perfectly into our p squared plus b squared equals h squared equation. Think of them like cheat codes for triangles. The most famous one of all is 3, 4, 5, because 3 squared, which is 9, plus 4 squared, which is 16, adds up to 25, and that is exactly 5 squared. Okay, here's your cheat sheet. These are the triplets you're going to see over and over again. If you can just memorize the first three, 3, 4, 5, 5, 12, 13, and 7, 24, 25, you will have a huge advantage. And hey, you notice those last two? They're just the first two, but doubled, which brings me to my next point. And this is where it gets really powerful. If 3, 4, 5 is a triplet, you can multiply the whole thing by 2 and get 6, 8, 10. That's also a triplet. You can multiply it by 10 and get 30, 40, 50. You can even divide it by 2 and get 1.5, 2, 2.5. The pattern, that core ratio, always holds true. So let's put this to the test. Imagine you get a problem like this. You've got two sides with decimals, and you need to find the third. I mean, you could plug this into the formula, but who wants to deal with squaring decimals? Not me. There's a much smarter way. Here we go. The perpendicular side is 12.5. The hypotenuse is 32.5. At first glance, finding x looks like a job for a calculator, but it's not. We can use our triplet shortcut. Okay, watch this. First, let's just find the simplest ratio between the sides we know. 12.5 is 5 times 2.5, and 32.5 is 13 times 2.5. So the ratio is 5 to 13. Ding, ding, ding. That sounds familiar, doesn't it? It's our 5, 12, 13 triplet. The missing piece of that pattern is the number 12. So to get our real answer, we just scale it back up. We multiply 12 by that same factor of 2.5, and we get 30. Boom, no calculator necessary. All right, we've totally got the side lengths down. But what about the angles inside the triangle? Well, it turns out that the relationship between the sides, that ratio we just used, is actually the language of angles. Now, don't let this table intimidate you. It's actually really simple. There are three main ratios: sine, cosine, and tangent. They're just fancy names for dividing one side by another. Sine is just perpendicular divided by hypotenuse. And see those other three on the right? Cosecant, secant, and cotangent? They're just the flipped or reciprocal versions of the first three. That's it. And because they're reciprocals, basically mathematical opposites, if you multiply any ratio by its partner, you will always get 1. Sine times cosecant is 1. Cosine times secant is 1. It's this really neat, perfectly balanced system. But wait, there's more. It gets even cooler. There's another layer of connection here. Tangent is really just the sine value divided by the cosine value. And since cotangent is just the flipped version of tangent, it must be cosine divided by sine. You see? Everything is connected to everything else. Now we come to the final, most powerful part of our toolkit, the master keys. In trigonometry, we call these identities, and they are incredible equations that are always true no matter what the triangle looks like. And they are the key to unlocking some really complex problems. So where do these crazy powerful keys come from? Well, you're not going to believe this, but we go right back to the beginning, back to our old friend Pythagoras, and it turns out this one simple rule is the parent of all three master identities. Okay, check this out. It's almost like a magic trick. We take our base equation, p squared plus b squared equals h squared. Then we do one simple thing. We divide every single piece of it by h squared. That gives us p over h squared plus b over h squared equals, well, h squared over h squared is just 1. And what are those fractions in the parentheses? We just learned them. P over h, that's sine. B over h, that's cosine. So our original Pythagorean theorem magically transforms into our first master key. Sine squared theta plus cosine squared theta always equals 1. See? It's not some new scary rule. It's just Pythagoras wearing a different costume. And the best part? Once you have this one key, you can basically generate the others. Let's take our new identity and divide every single term by cosine squared. Well, sine squared over cosine squared becomes tangent squared, and 1 over cosine squared is just secant squared. And just like that, we've unlocked the second master key. Want to see it again? Let's go back to that first master key. But this time, let's divide everything by sine squared instead. And what happens? The exact same logic reveals our third and final master key. They all grow from that one original seed from Pythagoras. And here they are, your complete set. We've just tidied up the second and third ones a bit so they all equal 1, which is a common way to see them. These three identities are some of the most powerful tools in all of mathematics for simplifying and solving really complex equations. So think about it. We started with one simple, elegant rule. And from that one rule, we built an entire system. We found shortcuts to avoid nasty calculations. We learned the ratios that act as the language of angles. And we forged three master keys to unlock complex problems. This isn't just theory. It's a real, practical toolkit for seeing the world. So now you've got the toolkit. The real question is, what problems are you going to unlock?